and welcome back to another episode with It's Dr. Dan. And today we're going to be looking at molecular orbital theory. Now, what molecular orbital theory is essentially an extension of the idea behind hybridization, where we get into a more realistic interpretation of how the atoms function. So this is an even more advanced method. So what MO theory does is essentially it's describing the distribution of electrons between molecules. Now, this is very similar to what we've always kind of imagined when we were talking about orbitals and electron configuration, where before we thought electrons were always surrounded by atoms, and we were able to describe that using atomic orbitals. Now, up until this point, we should know a few different things before kind of continuing with this video. You should have really good knowledge of Lewis structures, electron pair geometry, molecular geometries, so everything that's VSEPR oriented. I would recommend knowing a little bit about valence bond theory and hybridization and that viewpoint versus molecular orbital theory, which is a little bit of a different way of approaching the same type of problem. And we're going to be explaining some bonding properties that have been seen before. So one thing is like, where does this kind of come up? Well, let's say if we start something small, let's say with oxygen. And if you're to look at this molecule, well, oxygen seems to be something normal, right? We need it to be to stay alive. If I were to actually kind of go through and draw the diagrams behind this, especially after looking at the entire concept of hybridization, well, first thing is if I were to kind of look at that, well, when these molecules bond together, they're going to rearrange their electrons through a process known as hybridization, which we've talked about previously. Is the whole idea here is that we're going to try to lower energy levels so that way they can bond together. Now, when this happens, well, these different guys they will bond. They're going to make a couple different bonds as a result, meaning we'll have a sigma single bond that's going to form, but we also have that double bond too in the structure. So then we're going to have this interaction between the parallel p orbitals, unhybridized p orbitals, to make a pi bond. So sigma and pi together make a double bond. Now that's great. That's what we learned all about valence bond theory. But the thing is, there's something that's still not able to be explained, which is essentially when you run oxygen as a liquid through a magnetic field, it shows magnetic properties. And one of the things is, well, why would it do that? Why don't we show this? And let's say we run two different molecules through a magnet. So what we have is very cooled liquid nitrogen, and we're going to be pouring that through a magnet. Now, as expected, nitrogen gas, we see that it does not connect to the magnets on both sides of this. So there's nothing happening. The second that I put liquid oxygen over these magnets, now if we kind of look really closely, you see that it's fusing to the magnets, that it's sticking. Oxygen is magnetic? What? How come we don't see oxygen magnetizing to all the metals around us? How is that possible? Right? There's nothing that we kind of have to explain that at the moment. However, there was a concept we did mention not that long ago, which was all about the idea of paramagnetism and dimagnetism. Well, para was all about that whenever molecules had unpaired electrons, they were attracted to electrons. However, looking at my diagram, especially once I have everything bonded, there are no unpaired electrons within the molecule itself. However, oxygen actually does have two unpaired electrons. Where are they? I don't see them anywhere in the hybridization picture that we've discussed. So this is a problem. That means that hybridization is missing some kind of key component to it that is not actually able to describe everything. So we're going to be comparing when something's paramagnetic or diamagnetic by learning about MO theory and when this works. So just as a reminder, diamagnetic was whenever you had all paired electrons, and that's what oxygen looks like. So where do these two unpaired electrons I claim are coming from? Let's dive into the theory. First thing is essentially trying to compare the different theories that we've been talking about in terms of general chemistry. The first one that everybody learns about is valence bond theory, which is hybridization. Let's talk about that first, and then we'll go into what the differences are with molecular orbital theory. So, when we talked about hybridization, the entire idea with this one is essentially considered electrons localized in bonds between individual atoms. Whenever these bonds were created, it was mainly due to overlap of different atomic orbitals and hybrid orbitals. When this happened is essentially whenever you had an overlap of hybrid with atomic or hybrid and hybrid, we made sigma bonds. And whenever it was the atomic orbitals interacting with each other, we had pi bonds that we're making. Now, why is that something that was great? Is that it gave us the ability to actually explain the why for how Vesper structures work, meaning it predicts molecular shape by determining where most likely the regions of electron density are, aka their steric number. So it gives us a good thought process. The one downfall of this is that it essentially says that electrons are localized, meaning they're in one spot. So we need a ton of structures to describe resonance, which the whole idea of resonance is that multiple structures exist all at the same time. Bond order changes as a result. So it doesn't really do its best in explaining all pictures, especially being that resonance is a big part of how our body functions, especially if you kind of think of it in terms of like the peptide bonds and for a lot of different structures that we see in time in terms of like the pharmaceutical industry. So, when we're comparing this to, let's say, molecular orbital theory, well, what's the difference? Well, this theory kind of tweaks that process. Well, what if instead I say, okay, let's say the electrons are delocalized throughout the molecule, whereas all of the atomic orbitals are working together all at one time. So, when that happens, the atomic orbitals are going to instead create molecular orbitals. So, if I have multiple atoms all in this molecule, they're all working together to create an entirely new orbital. So valence bond theory was all about one single atom hybridizing. Molecular is the whole molecule is changing to make different orbitals. Now, when this happens, those atomic orbitals are going to interact to make what we call bonding and anti-bonding interactions, which are going to be different types of orbitals that are going to be forming. Now, what this is going to be used for is to help us predict the arrangements of electrons. So, not just the structure, but exactly where's the probability of these electrons being located when we try to think of quantum mechanics. So, it's going to give us essentially us assuming where the lowest energy possibility is. So that way we can get an idea of what the orbital picture looks like so we can know how a molecule truly behaves on the electronic level. So let's take a look at both of these. So the first thing when we get to MO theory is that the whole idea behind this is that we need to calculate the orbitals for the entire molecule. But don't worry, there's no math with this one, for at least for general chemistry. This is something that's generally reserved for research institutes or very high level graduate students who are trying to, hit their head against the wall a little bit to understand all the basics. It can be some done in general chemistry, but usually it's on a very, very simplistic level. So where does this all come from? Well, the whole idea is that what we're trying to do is solve the Schrodinger equation. And the thing is with that is that it's actually pretty much impossible to solve it exactly. All we can do is try to make an approximation because the electrons are moving so fast. There's too much uncertainty for us to know exactly where they located at a given time. So when we're trying to look at this thing, we can approximate what the wave function is, meaning we can try to figure out an idea of what the shape is or where the electrons most likely are. So, what is this kind of analogous to here is that electrons around these atoms are limited to discrete quantized energy levels. So, it's the same kind of idea in the molecular picture, too. The only difference is that, well, once we kind of assume that all these atomic orbitals are working together, is that we can actually figure out where the electrons are most likely located in a molecular orbital between this. So if we square a wave function, we can figure out the probability and plot it of most likely where these things are. Keep in mind when we're doing this, it's going to be very similar to electron configuration, meaning it's still going to follow the Pauli exclusion principle, the Aufbau principle, where we start with lowest energy first and fill up, and we'll still do our Hund's rule where we do degenerate orbitals as well. So it's almost the exact same thing as what we've been doing before, but just some different symbols with sigma and pi bonds. So let's dive a little farther. The first thing is where is all this coming from? So whenever we're looking at these, it's all talking about what we call the linear combination of atomic orbitals, or LCAO for short, which is a more common acronym. So whenever we talk about this, in a sense, it's just adding up all the atomic orbitals together to create all the molecular orbitals. So say, for example, if I have two atomic orbitals going in, I'm going to end up having two molecular orbitals coming out. Now, the difference between valence bond theory is that valence bond theory only combined the orbitals of one atom. This is talking about two or three or four combining together to make a giant molecule. In our case, we're just going to stick with two just to make it easy because we're beginners, right? We're just starting off to understand. So the whole idea of where this comes from is actually based on how waves worked. So if you kind of thought of a wave, well, if they were in phase with each other, so both starting at the exact same point, like I have here on the left-hand side, they would construct or add up together. Or if I had them slightly out of phase with one another, where one of them's down, the other one's up, they will deconstruct with one another. So, with the same idea here, orbitals do the same thing. Orbitals can be in phase or they can also be out of phase. And it's all based on where the electron is located in a given part of that orbital. So, if it's in one region, it's in phase. If it's in another region, it's more out of phase. So, there's different areas where most likely it's going to be at one time, right? It's almost like a coin flip. So when we're trying to figure out where exactly is it, well, as a result of this, is we can create two different types of orbitals every time two atomic orbitals interact. So remember, two atomic orbitals, we're going to get two molecular orbitals. So every time, let's say you have S and S interact, what you're going to get is one orbital is going to be a bonding orbital, and the other one's going to be anti-bonding. Now, what's the difference? Does that mean one doesn't even interact? Not entirely. It's just a more of a vernacular word that's being chose by the community. So the whole idea here was whenever we have bonding, is that this is the lower energy orbital, meaning that it's going to have the two nuclei. They're going to be interacting together, and it's essentially like making a sigma bond or a pi bond that's interacting directly. With that, it's going to have a lot more electron density. It's going to be lower energy, very, very stable. Whereas whenever we have anti-bonding, well, this is one that is a little bit higher in energy. It's a little more unstable. It's actually kind of working against the nuclei being in the ultimate place. So it's kind of like a checks and balance type of system. It's like one of them's working really well. The other one tends to work a little bit out of character, a little out of sync. So it's destabilizes it. So it's a give and take, right? You can't just have a million bonds forming between the two atoms. It's a low energy and a high energy. So what does this look like in terms of a picture? Well, if we're talking about two different nuclei, so let's say I have atom one on my left and then atom two in green, so purple and green here. So both of them have an s orbital that are interacting with each other. What exactly is going to happen when they interact? Well, if they're both interacting on this x axis where the nuclei are, one orbital is going to end up adding together, right? So creating our sigma bond in the bonding orbital. And then being that if we started with two atomic orbitals, well, we must have another orbital as well. So we're also going to create an anti-bonding orbital where they're out of phase with each other. So we're always going to have two going in, and then we'll have two coming out. So we have a higher energy, the anti-bonding, and then the lower energy bonding. Now with this, right, we can see they're both sigma. So sigma s, because we're talking about the s orbital. The way that we tell the difference is sigma with a star and without a star. So when it has a star next to it, that means anti-bonding. It's really high energy. Wherever we have it without one, that's telling you it's bonding. And this can happen with different orbitals as well, not just s. So we can go a little bit farther. We can do it with p orbitals too, because they can also interact on the same axis too. So let's say if we're thinking of the same thing, well, if I have px and px going together, so two atomic orbitals, well, how many molecular orbitals do you think are going to come out? And if you guessed it right, it's going to be two, right? So once again, we're going to have a bonding and an anti-bonding. So when they're head to head or overlapping, just like hybridization, that's when we make the sigma bonds. So the way to kind of tell when it's bonding, you can kind of see the overlap between the orbital, like right in the middle here. We can see all that really connecting with each other. Where whenever the orbitals ended up being out of phase, they end up not matching in terms of color. They can't actually create a stable bond. So it's very high in energy. Let's see what other types we had. So we had sigma, we also had pi. Let's look at the other. So whenever we had pi bonds, the whole thing about these is that they had to be parallel with one another, so facing each other. So when we had that parallel orbital connecting, well, once again, let's say if I were to look at the py and py together at the top, two orbitals are going in. How many need to come out? It's going to be two. Same thing with pz, right? They're both in line with each other, or sorry, it's more in line this way, right? We can see them together. So it's going to be the same general idea. So let's look. So with these, right, they each make two sets of different orbitals. So we can see like one almost looks like a butterfly with alternating wings. And then the other two, when they overlap and merge together, it helps create that delocalized pi bond that goes between two individual atoms. So just to kind of like think about that, well, where are the atoms? Well, let's say if the atom would be like kind of right in the middle of each of these orbitals. So where I'm putting these red dots would be like where the nuclei are in reference to one another. So it's all about like kind of where are they in the different structures. We're always going to have two individual orbitals making two others. So let's go through some examples on when this is possible because I'm sure by now it's a little confusing to follow. When can we make each one of these different orbitals? So the whole idea here is when we're looking at them. So if you're given a pair of orbitals, you're just trying to figure out, well, can they form and can they not? Well, what could we make if you remember, right? Well, we had sigma and pi, right, from hybridization. So sigma was all about overlap and pi was about being parallel. Now, the only difference here is, well, what kind of orbital can it make? Can it be sigma bonding, pi bonding or anti-bonding? Or maybe it's even possible where it doesn't make a bond at all, right? So if it doesn't fit either definition, so that's possible too. So let's say if I were to look at this first one, so I'm adding together two 3px orbitals. So we see them over here on the left-hand side. And the whole idea here is, well, they're facing each other. So it says facing only. So being that they're facing each other, these two orbitals are going to come together. And we can see that they're adding together, right? They have the exact same color as one another. So what type of orbital do you think they're going to be, being that they're going to be overlapping? Well, the first thing is well, it's definitely going to be sigma. But is it bonding or anti-bonding? Well, it's going to end up forming one where they have a ton of overlap as a result, right? So, being that they have that overlap, how can we label that? Well, that's going to be a sigma bond. And to be more specific, we could say, hey, that sigma 3px, being that they were the ones that were forming that individual orbital that are there. So we can put that in our details. Now for the next one, it says we have px and py coming together. So how about this one? Well, if I try to overlap them with the side, well, before whenever we talked about overlap, they were always on the same axis and pi was always on parallel axes. So it doesn't really match either of our definitions. So what's going to happen here? This is when we're going to make no bond, being that it doesn't match them on the same or parallel. So it's either together or together, right? It's one or the other. So what about this one? So this last one, okay, they're both parallel. So what does that tell us? Well, it's definitely pi. Are they in phase with one another? Well, if we look at the colors, we can see that they're opposite of one another. So what does that mean? Is that they're going to be out of phase with one another. So what should this make is it should be pi 3py based on the original orbitals we were starting with. So if we were to try to draw that the best we can, we should see those butterfly wings that we had previously. And this is usually information that you're always given is what orbitals you're starting with, and you trying to predict, okay, well, which one is it? Or you're just filling in the different orbitals as well. So this is kind of one of those ideas of just how does this whole thing work? So this is the theory behind it or the basic idea. So where exactly can we apply this? Well, the whole concept with this thing is that we usually will fill in molecular orbital diagrams to show this, meaning that we're going to be trying to see how are all the different electrons going to be filling in, starting at the lowest using the Aufbau principle, and then filling it all the way up to whatever the highest levels are, and that's where we can get the paramagnetism and diamagnetism that we've seen in the video from before. So that's where the second part video is going to come in, where it's going to go to how to fill in molecular orbital diagrams. So that will be the next video to try to cut this up a little bit for everybody. All right, thank you so much for listening, and I'll see you guys in the next video for the molecular orbital diagrams, which will go mainly through practice problems and examples. Okay, see you all soon. Bye.